Hi, everybody. For today's very brief lab lecture, right before the actual Chapter 4 lecture, I do want to point out that the module is now open for this week's lab. Lab number 5 is basically your lab final. And what you're going to do is you're going to be given a bunch of data in the lab documentation, and your task is just to figure out what to do with it. And in all of the experiments that you've done this quarter, you've seen how to work with this data. So if I go here, so like it's only 4 pages, and it's just like here's some data, here's some data, here's some data. Do something with it, and then here's what the pages look like. I'm going to give you an unknown. You tell me what's in the unknown, and so you're going to determine ethanol based on the preparation that it shows that. You're going to determine tartaric acid, and then you're going to determine sulfur dioxide. And these are just components that are in wine. You can read the introduction to learn more about it. Obviously, we know that ethanol is in there. It's a fermentation product, and it's kind of the whole point of why people drink in the first place. Tartaric acid gives wine a very specific tartness to it. And then sulfur dioxide is used as a preservative. And you will be determining the concentration of all of those in this documentation. Down here, I have a giant table, which is just totally blank. This week, you get to make your own table. So you're going to need to incorporate the data from the data tables in here somehow. You're going to need to label everything and tell me what you're doing, and then provide the answer up at the top in these boxes. And then finally, tell me what you did using 3 or 4 sentences. Okay. When I did this experiment, I had to create all the data from scratch, which means that I was just making the key, so I made what I expected to do with like the bare minimum. And if I can do the whole thing with using like this much space and maybe 2 sentences, then you should totally be able to do that using twice as much stuff, and that's fine. Because I know students sometimes tend to explain a little bit more than they need to, which is the intent. Don't go farther than the bounds of this box, and do not go outside of the bounds of the shaded area for anything you want me to grade on any of the pages. They should all be the same size. Has the last lab already been graded? No, I'm still working on it. I'm hoping to get that finished by this weekend. I've been working on the quizzes and the midterm, which I feel like are more important things that need to be done since those are coming up. Anyway, that's the lab. That's really all I have to say about it. You can access it now. I suggest that you do so. And the grading scheme at the bottom will tell you all about how the points are assigned. You'll notice that this one's actually worth 30. Yes, you can get extra credit if you do everything perfectly. That being said, I am looking for specific answers for this one. So if you are outside the bounds of the correct answer, then you don't get full credit for it. And so that's why I'm offering extra credit, because it's actually going to be very hard to land on the target number if you make any mistakes. So full credit is awarded if you're plus or minus 5 on the last sig fig. I'll give you 2 out of 3 if you are plus or minus like 5 on the second to last sig fig, and then if you're too much further away than that, I might give you 1 or 0. And you can see how making even a single mistake in any calculation could throw off your answer by any number. Oh, I put in 24 instead of 29. Well, now you get 0 out of 3 for that part of the assignment. So this is a very quantitative analytical sort of assignment to test whether you have learned what you should be doing for from the previous labs, or whether you're just fumbling your way through, I guess we'll say. The other thing I do want to mention is that I am grading you on neatness in some capacity. If I look at your data table and it just looks like, what the hell is going on, I'm going to give you 0 out of 5. I'm not going to spend more than 2 or 3 minutes trying to pick together what you have, because I have 72 of these. Okay, so please make sure that you are writing out tables that have labels Any table that has numbers in it and it doesn't have a label in it, I will just deduct points for. You've seen how my tables have looked like this quarter, how everything is very clearly labeled and describes what I want you to put it in there. I want you to do that, because that's what your lab book should be like, and I have provided you with more or less a blueprint, so you can go back to the previous labs and copy what I did, and that's totally fine. I am going to leave it up to your interpretation how you do it, because we haven't really had any practice with that, and so this is part of your assessment. And yeah, I did say neatness. And that's pretty much it. Each of those pages that I showed you is worth 10 points, for a total of 30. You can see the point breakdown on the side here. Good luck, we're all counting on you. That's pretty much it. Any questions, let me know in the chat. Now you can see why I was like, oh, I don't want that just to be our lab lecture today, because that's literally all I had prepared, was 6 minutes worth of, all right, you know what to do, so do it. All right. If you have questions about the content, we can answer them as we go along. I do want to just continue on with the lecture so that we can finish chapter 4 this week. Yeah, I'm gonna go until 3. So if you have places to go, remember that this video is uploaded to YouTube and you can watch it at your leisure. But I am gonna use the whole 2 hours today, like it was a normal lecture, to go over the content, just because I need to get the content covered in order for me to be able to test you on it on Monday and on the final. Fortunately, there's not terribly much left, so I believe that I can get through this today and tomorrow. So let's keep going. In the previous section, what we did yesterday was I had you draw lots and lots of Lewis structures. And then I drew you the Lewis structures, and hopefully yours match mine. If you have a Lewis structure that has multiple bonds in it, sometimes there is a way to shuffle electrons around and have different arrangements of bonds, but they still all satisfy the octet rule. And you have to decide, well, shit, which one of these is right? For example, here's CO2. If you look at the one on the left, it looks symmetrical and nice. If you look at the one on the right, it looks not symmetrical and weird. And that's just our cognition playing tricks on us and saying, oh, we like things that match, but we don't like things that don't. That's not a very good systematic way to make a determination of which of these is actually better. If we could base this on evidence of some sort, that would be much more reliable. So what we need to do is devise a method that tells us why the left structure is the correct structure and why the right structure is not. And so that's the first thing we're going to do. This is the concept of formal charge. Formal charge is not a thing that exists. Formal charge is a bookkeeping model. And so when we do formal charge, it doesn't mean, oh, we have a positive charge where the plus is, or a negative charge where the minus is. Charge is much more granular than this. But what this method does is it tells us how to adopt the best Lewis structure if we are given a bunch of choices that appear to be equivalent. And so here's how this works. To calculate formal charge, we're going to determine the charge on each atom if each of these bonds just gets split down the middle and we divide the electrons equally. So what charge would the atom have if all the electrons were shared equally? And so the other way to do this is to simply just circle an atom, like so. And we're going to count all the electrons that we circled with the bond part that we circled, only counting each bond as 1, because we're only going to count the electrons that are shared. And so the way that this works is to calculate formal charge, we do valence electrons at the start minus how many electrons the atom we have circled currently has. And we're going to retain the sign, not return the sign. That doesn't make any sense. So let's calculate this. So over here, to calculate the formal charge, I'd count how many valence electrons does oxygen have? Well, it starts with 6. How many electrons does it currently have? It has 1, 2, 3, 4, 5, 6. So the formal charge on this oxygen over here is 0. But let's go calculate the formal charge on this oxygen over here. All oxygens start with 6, but how many electrons does this guy have? 1, 2, 3, 4, 5 available. So the formal charge on this oxygen on the right Lewis structure is +1. If I do the formal charge of this oxygen right here, I would get 6 minus 1, 2, 3, 4, 5, 6, 7. I get a formal charge of -1. This oxygen right here is identical to this one that was over here on the left, so its formal charge is going to be 0. And then finally for carbon, carbon starts with 4 valence electrons. There are 4 bonds to it, so its formal charge will be 0 here. Here there's also 4 bonds, so its formal charge will be 0 as well. So this is our formula. Remember that you want to use this formula to calculate formal charge. How many valence electrons does the atom start with? How many valence electrons does it currently have, counting bonds as 1, and then subtract the 2. Formal charge is only for singular atoms. That said, if you add all the formal charges together, you should get the overall charge. So since these are molecules, the molecule has a total charge of 0, so all your formal charges should add to 0. And if you look at it, you can see that that's the case here. Alright, I'm going to clear the screen because all of these numbers are going to appear in just a second here. Boop. Now that you've calculated the formal charges, and that's what these numbers in green are, so these are my formal charges. Which one is better? The best structure has charges that are not separated. So for instance, this Lewis structure on the right is the effect of me taking an electron from oxygen on the left. I pushed the wrong thing. It is the effect of me taking an electron from the left and putting it on the right. That seems kind of weird. Why would we take electrons from oxygen and give them to another oxygen? There's really no reason to do that. We're separating charge, and the lack of positive charge on one end should be countered by the lack of negative charge on the other, and so they should draw together, if an option exists. Oh, excuse me. So the closer you can get to everything having 0 formal charges... Oh, that's the wrong color also. The better. So that being said, this one is the best structure. Sorry, drinking water there. All right, let's do another example here. Here's 2 different ions, and these are actually in brackets with a -1 charge, but I didn't include that for some reason, and that was silly of me. So let's do that right now. And I'll write the formula again here. So valence electrons at start minus current electrons. And what I want you to do is determine the formal charge of all of the atoms for the structure on the left and then the structure on the right, and assign them numbers, so like +1, 0, -1, -2, +2, whatever. Type it in the chat when you got it. And you're going to do this in the same way as the last one, but the numbers are going to be different. Because the previous one had C's and O's, this one has S's and N's. So do the calculation. Tell me what you get. Type it in the chat, and we'll go over the answer in just a second once I fill up my water. Alright, a bunch of people are coming up with the same answer of, huh? But they're the same, even though the structure is different. And yeah, we're going to talk about that in a second. But I'll give you another little bit to finish up. We'll talk about what to do. Alright, let's calculate the formal charge for each of these. So for nitrogen, if I circle it, I start with 5, but I have 1, 2, 3, 4, 5, 6. So its formal charge is -1. I'm going to try and get a different color for each of these so I can make it a little easier to see. Boop, 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 boop. Carbon is 4, starts with 4, has 4. Formal charge is 0. We'll do whoop. Sulfur starts with 6, ends with 1, 2, 3, 4, 5, 6. So I got negative 1, 0, and 0. Okay, that's interesting and all. But let's go over to the other side here. Ooh, that's the wrong pen. I hate that pen, by the way. Mostly because the pressure tip on this is really sensitive, and I always just get the thickest setting. Alright, so this is 5 to start with. This guy has 5, so now I have a 0 on the nitrogen. Same thing for carbon here. And then for sulfur here, well, that's a thing that I did. There we go. So 1, 2, 3, 4, 5, 6, 7. It has 7. So there are formal charges, and let me put my brackets back here. All right. Sorry. There we go. Okay. How do we determine which one is the correct Lewis structure? The answer to that is that if we have a situation where we have the same result in both cases, but we have a number that we can move around, let's think about where the number should go. What property would govern where a negative charge would prefer to be? It's right there on the screen. What property dictates how well atoms attract electrons to itself? Yeah, there you go, electronegativity. So we're going to give the negative one to the atom that is more electronegative, which is what, N or S? It's not S. Yeah, it is N. N is really electronegative. Yeah, I narrowed it down for you, right? So, if N is more electronegative than S, this must be the correct structure. Now, remember that if you have a charge on your ion, that all the formal charges will add up to that. So if you get a negative 1, and there's... Oh, excuse me. And there's just no way to get rid of it, like you cannot get a structure with all zeros, make sure that you didn't forget like a negative ion charge somewhere. Because those will match. Alright. This slide is just a reminder that formal charges don't exist, like I said. Formal charges are just a sort of tool that helps us dictate which Lewis structure is better than the others. Alright, so here I have a bunch of different structures for you to draw. And so what I want you to do is draw NO+, SO3, O3, and then phosphate. Make sure that you minimize the formal charges on these as best as you can, especially for SO3 and phosphate. Okay, so draw these Lewis structures. I will come back and draw them with you in just a moment. But I do want to give you a chance to practice this because the whole point of Chapter 4 really is to name stuff and then to draw it. So I got to give you enough time. So go ahead and do that, and we'll be back in a bit. Alright, I'll give you a few more minutes to finish up. I'm actually drawing a bunch of Lewis... I hit the wrong button there. I'm drawing a bunch of Lewis structures here to show you, so when we get back, I'll show you all of those in a second here. In some cases, you're going to find that you can't actually do anything other than just one structure. For example, NO probably only has one acceptable structure. And formal charges help illustrate why. Even when there's like, oh, how do I make everything follow the octet rule? There's only really one way to do that. So we'll go over that answer in just a second. Alright, let's go over the answers here. So, oh, hold on, I want to zoom this in so I don't spoil all the answers right away. Oops, hold on. Alright, so when you draw the Lewis structure for NO+, you get 10 electrons to work with. However, there's really only one way to draw this. I'm going to draw the other things that you could try to do in red here. And what you'll find out is that you run into issues. So, obviously, this is where you got to start. You got to start by doing that. And if you fill in the electrons for the outer octets first, you have to have a choice between O or N. O is more electronegative, so you should probably start with its electrons first. And then you get to here, and you're like, well, shit, what do I do now? That's way too few electrons. And your options really are only to say, okay, if I do this, then I get the structure on the left here. But if you did something crazy like, say, this, would this be okay? And this is no good for a lot of reasons, it turns out. So first of all, oxygen doesn't have an octet. There's only 6 electrons here, so I should really just do this right off the bat. But we've been talking about how you don't always have to have an octet. And yeah, that's true. But let's consider formal charges here. So if I calculate the formal charge of this nitrogen in this position, I get this. Starts with 5, currently has 6. Over here, my oxygen, though, starts with 6 and currently has 4. Looking at my formal charges, that should be an obvious no-no. Like, why would I have a minus on the nitrogen and then positive 2 on the oxygen? That already doesn't make sense. If I can take some electrons, I should. Now, so this is obviously no good. Now, the other thing you might look at is say, oh, okay, well, hold on. How about I just put the positive on the nitrogen and try and get the negative on the oxygen here? So what if I did this instead? So I move these electrons in. And now if I calculate formal charges, ooh, that's a lot better, right? Well, there's a problem with this too. And that problem is that, remember how we said that you can't have more than 8 electrons on a period 2 element? If it's period 2, the most electrons it can hold on the S and P subshells is 8 total. So S2 and then P6, total of 8. This currently has 10 around it because I shared 8 electrons through the quadruple bond, we'll call it, and then it still had 2 already. So this doesn't work either. And again, you can't make quadruple bonds. Yeah, I'm just showing you all these reasons why these things that I just told you don't work still don't work now with our model. So you might be looking at these and thinking, ew, I would never have done that in the first place. And that's good if you did. But what I'm trying to avoid are situations where you think, well, he hasn't said we couldn't do this. And now I'm showing you these extreme cases where it's like, oh, this is obviously bad. Here's why. Because you might have the intuition to say, this looks weird and I don't like it. But you might not know how to, to elaborate on that, for example. And these are some reasons why. The other thing that's important to comment on is that this looks really weird on oxygen. And it's very off-putting to students who are first doing this formal charge method and saying, oh, I want to put the negative element or numbers on electronegative elements, and I want to put the positive ones on the ones that are less electronegative. Oh, wait, in this case I can't, and it's the first example he gave us. What the hell? And the answer to that is sometimes this happens, and there's really not that much we can do about it. If we try and move that positive 1 formal charge somewhere else by changing the Lewis structure, we end up getting other invalid Lewis structures for various reasons. Like we make formal charges bigger, or we end up with breaking the octet rule, or whatever. So I guess what I'm trying to say is at the end of the day, I'm throwing a lot of rules at you, and sometimes they will work together, and sometimes they won't work together. And what it will fall upon you to do is, after you've done a ton of these examples, you'll develop the ability to say, oh, okay, this is probably the better of the two choices. And that's really all I can ask, because these models aren't super perfect. Okay? We're going to see that in a second here when I talk about ozone. All right. Down here I have SO3, sulfur trioxide. I drew 3 of them. I could draw one without a double bond at all, I guess. I could put that up here. So if I just do this. All the numbers that are in red are my, I can't add to 3, it turns out. All the numbers in red are formal charges. Problem with this structure, as you can probably see, doesn't have an octet. That's no good. We want to try and at least satisfy the octet rule. The ones on the bottom definitely have an octet, so this one's no good. This has an octet, and all the rest of them have an octet, so this is okay. This is okay. This is okay. But one of them is better than the others. And it might look a little weird, because why would I have all these triple bonds to sulfur here? Well, if you do that, then the formal charges on everything become 0, so that's a plus. Secondly, you can also make that many bonds to sulfur, because sulfur has extra orbitals for electrons to go into. Sulfur is in period 3, so it's allowed to exceed the octet rule. So that's also okay. I would say that this is the best structure, because we've minimized formal charges and we didn't break any obvious rules. Now, hopefully you drew that one. I would say that this is probably the most likely candidate to be drawn without considering, oh, I can expand past the octet rule. Mostly because we didn't get to do those examples yesterday, and I don't know how many people actually did them. Hopefully you did them. All right, the last one we got is ozone. I'm trying to hide that one over there because I want to talk about it specifically. With ozone, if I want to make sure I don't break the octet rule, there's really only 2 ways to do it. But then I get this weird situation where they're both exactly the same, and then I seriously have no way to differentiate them. Before, I could have just said, oh, okay, I have a -1 on N and a -1 on S. I'll put it on the more electronegative atom. But here, they're all oxygen. Which one's more electronegative? Well, they're all the same. Is there any way for me to get that positive off the middle atom? And it turns out not really possible without kind of cheating. We'll talk about it in a second. Valerie uses the same OpenStax book. Yeah, we all of us use the same OpenStax book. For 160 whatever. So these two structures we're going to come back to in just a second. So I'm going to save them in a red box. So we'll just do this. Now, the idea that you have in chat there is actually a really good idea. What the hell is preventing us from doing this? Because now if I calculate formal charges, they're all 0, and this is super awesome. Except there's already this giant X next to it. Why is that not allowed? And this is the part where models break down. So there is a very specific reason why this doesn't happen. And unfortunately, for me to really explain it in the best level of detail that I want to, we have to talk about geometry. And we haven't actually done geometry yet. It's coming up in the next section. But for the red arc that I put here, what angle is that? Think back to your geometry class. This is an equilateral triangle. All these oxygens form 3 corners of a 3-threaded entity that are all equidistant. Yeah, there you go, 60. So this is a 60-degree angle. What we're going to learn later on is that the preferred bond angle for oxygen, or any atom really that has 4 things coming out of it, 2 of these are bonds and 2 of them are electron pairs, because electron pairs take up space too, right? This is the preferred angle, 109.5. If you take your hands and put them in front of you at about a 109.5 degree angle and say, this is where my electrons push themselves apart to, and then you contract your hands to be about 60 degrees, and you'll notice that you moved your hands a lot. Like, they are significantly closer. And remember how Coulomb's law works. As R decreases, the force between them increases. It turns out 60 degrees is far too close. And so what ends up happening is that this structure can't form. It would love to form, trust me. This is a really good structure on paper. But in reality, we don't observe it because of the bond angle being just too tight. And so this is something that's called ring strain. And we'll talk about ring strain in 262. So in organic chemistry. Because some molecules actually do manage to do this. Carbon actually will do this. However, the compound that it makes, cyclopropane, it's explosive. Like, it will just explode on its own. Yeah, we're going to talk about bond angles. I'm going to tell you the bond angles. I don't think I'm going to test you on the numbers because I just don't have a way to, like... I can't enter a degree sign into Canvas, for example. Or you can't, I should say. I can enter. Yeah, good job, Carbon. Way to blow things up. Anyway, that leaves us to these choices over here for ozone. What the heck is the better choice here? Well, I mean, we could make the argument that if I just rotate this guy around, then they're the same thing, right? But in reality, are they the same thing? Not quite. We're going to come back to that in just a second. I didn't do phosphate because I ran out of space, there's no room down here. So what I can do here is I don't want to erase my my ozone there. So we'll get rid of this. And I'll do phosphate really quickly here. I have the wrong color. That's my formal charge color. Here's just some Lewis structure. If you double bond both sides of ozone, then this oxygen in the middle will break the octet rule. Because that would totally solve all of our problems. Except for the small fact that I would have 10 electrons around oxygen. Which, that's not okay because I can't put them there. I wrote the wrong letter. I'm only going to do a few of these because, as you can see, there are so many different combinations. Let me do the one that has no double bonds here. Alright, so I'm going to go do formal charges on these. And anytime we have a double bond with oxygen, its formal charge is going to be 0. So here's a bunch of zeros here. Anytime I have an oxygen with a single bond, it's going to be -1. Because these are all just the same calculation over and over and over and over. And then we got to play with this phosphorus thing here. So I know that they're all going to add up to -3. So I could just use that to do the math here. Or I could do the formal charge. This would be 5 minus 6. This is 5 minus 5. And this is 5 minus 4. Now, right off the bat, what we want to do is minimize formal charges. So this one has the most zeros in it by far. Oh, this one actually has 2 zeros also. So this one's out. We'll say that this one's no good. Now, between these two, which is more electronegative, P or O? And you should immediately say, oh, it must be oxygen. So that makes this one the better one. And this one's just okay. Now, does it matter which double bond that I make? Could I have double bonded the top one, the left one, the right one, whatever? And the answer that I have for us at this slide, which is going to immediately be invalidated, is, sure, just spin it around, rotate it. I can put the double bond on the top, I'll just flip it around 180 degrees, now it's on the bottom. Flip it around 90 degrees, now it's on the left. And then what we're going to learn immediately on the next slide is that, well, in reality, it's not quite like that. And that when you have options for moving double bonds around, but get equivalent structures that are just symmetrical, there's a special property involved with that. And it's called resonance. And we'll talk about resonance after the break. So let me put ozone back on the board here. We're going to talk about ozone in more detail once we get back. Let's do this. There is no timer. Time doesn't exist. Oh. I was like, what the hell is that weird sound that I'm hearing? It's power tools outside. They're pressure washing the apartments here, so. Start the timer. Start the music. If I could find the music. There it is. Alright, I'll see you in a bit. What? What? Yeah, I'm trying to find appropriate fanfare. Hold on. Just a second. I don't even know. I know. I'm so excited. I was just like, wait, what? Yeah, where is that? Let's try this. I have no idea what this YouTube will entail. There we go. Oh, you can't hear it because I have this unmuted. Hold on just a second.
Bam! Just like that. That's all there is to it, Dustin. That's all there is to it. A winner! Just like that. We'll be right back on our Price is Right. Don't go away.
All right, that was fun. That'll never happen again. I'm probably going to get another copyright strike, so hooray. Whatever. Yeah, that wasn't even planned. I just hit the button, and I was like, you know, one of these days I might get it. I wasn't even, like, trying. Normally I try, like, I sit there and I tap my foot to it, and then I hit the button and I'm always off by a little bit. I didn't think it was possible. I thought it was, like, a frame issue with, like, how the refresh rate is on my computer, but no. No, apparently it's a thing that can happen. Sorry, Leia, I lost your question in there while I was being a goofball. So let me clear this real quick, and we'll do SF6 real quick, or was it SCL6? They're the same, really. But because because sulfur can break the octet rule, yeah, it's totally amazing what you can do when you stop trying. You should definitely try, by the way. Like, don't just go into the final and be like, yeah, whatever. So because sulfur can break the octet rule, we can just put as many things around it as we want to. I'm kind of crammed on space here, so... There we go. That should be 48. 8, 16, 24, 48. Yeah. So, because I can break the octet rule with sulfur, I am allowed to make multiple bonds. And if we do formal charges really quickly, you'll see that all these chlorines are all 7, minus 7s. And then the sulfur here is just 6 minus 6, which is 0. And so you're all set. So it turns out... Oh, I was drawing behind the thing here. Sorry. So it turns out this is actually a perfectly valid structure. What you're going to see with a lot of these higher valence molecules, so things like that have 5 and 6 entities coming out of them, they're almost universally going to be single bonds. And that's really common. So if you see like PCl5, it's all just single bonds. When we get to geometry, you're going to see a bunch more of these. Strong recommendation, if you go to the textbook and you look at the problem sets that say things like, hey, draw the Lewis structure for PCl3, and then PCl5, and then TeCl4 2-. There's tons of them in there, and you should draw as many as you can, because it's going to help you a lot out today. We're going to do polarity at the end of geometry, because I got to explain how to do shapes first, before I can help you explain polarity, because polarity depends on shape. You actually already kind of know how to do polarity, in the sense that we've discussed how to do bond polarity. So, like, S is less electronegative than Cl, so it would just point in this direction. But I could do that along all these bonds here. And the end result that happens is the sum of all these. We're going to talk about how that works later on. Let's go back to ozone. Oh, ozone was just hiding down here. Here's my ozone here. No, it's gone forever. I must have hit clear. All right. Well, don't mind me. I'm still just I still have this 10 minutes on my screen here, and I'm just still like, hee hee. Let me clear this out of the way there. On the board, I have two resonance structures. I've spoiled the answer here. I have two Lewis structures of ozone that we determined were pretty much identical in every way, except maybe like you could rotate them or something. Let me put the formal charges back up here real quick. And sure, yeah, they're rotationally symmetrical, but at any given instant, what does a molecule actually look like? Does it look like one or the other? And it turns out that the answer is neither, believe it or not. In reality, what molecules do is if you have a structure where it looks equivalent and all you're changing is where the double bonded electrons are, then in reality, the molecule is actually the average of those structures. And so this is called a resonance structure. What a resonance structure is any pair, or even more, so you could have 3 or 4 or 5 different structures where the only difference between them is where you have this extra bond. Now, obviously, you need to have other electrons that make that difference too, so I'm going to highlight the electrons that would move. For instance, if I were to move this pair of electrons into this double bond, now this oxygen in the middle has too many electrons around it, so I'd kick these off in return. And that's how I would get the structure on the right. What I'm doing with my arrows here, this is called electron notation. This is pretty much what you do in organic chemistry. So if you are going to OChem in 261, 262, when you play with mechanisms, you're going to push electrons around all over the place, and it's super useful to understand how they move. If you can do a different structure, so this is my different structure. If I can make this structure just by moving electrons around, then it's a resonance structure. Now for the ozone, there's only 2 possibilities. And I believe I put in the little notation. There it is right there. Whenever you have resonance structures, what you do is you add this thing, this double-headed arrow, to indicate, oh, these 2 structures are resonance structures. And what that means is that the actual structure is the average. Ah, here's the cursed pen again. Hold on. If I could just select the damn pen I want. There we go. So the actual bond... Not bond, sorry. Structure. Is the average of the resonance structures. And so what that means is that when we look at what the bonds are, the bonds end up being averaged based on what resonance structures we draw. So I'm going to do an example of that in here to show you what I mean. And it didn't pop up correctly. There we go. So I need to first... Oh, we'll get rid of this. First, I got to draw those structures really quickly. Not in that color, though, because I need that color for... Oops. Alright, so there's the one that's on the left. We'll do the one that's on the right here. And I do everything... Oh, I forgot this guy up here. There we go. Alright, so what we're going to do here... So these are resonance structures, so I'm going to draw this arrow towards them. Now what I'm going to do is we're going to examine the average bond length in the molecule. So this is a double bond. And this is a single. What we're going to do is I'm going to select a location like this. I'm going to select the same location in all of my resonance structures. And what I'm going to do is I'm going to count the number of bonds and divide it by the number of structures. And when I do this calculation, this is going to give me my averaged bond strength. I'll get to your question in a second, Leah, sorry. So for ozone, what we've got going on here is on the left bond we have a double bond, and on the right bond we have a single bond. So I'm going to count the number of bonds that are there. So double is 2, and a single is 3. So there are 3 bonds. And those 3 bonds are spread over 1, 2 positions, or 2 structures. So in the actual structure of ozone, so like the thing that exists, not like a picture, but if I had a molecule of ozone and I handed it to you, what ozone would look like was as if it had 1.5 bonds in each position, and not 1 bond on one side and 2 bonds on the other. So if I had a way to draw that, it would be like this. Where in this dotted line were 2 electrons that were just kind of floating around. That's really the best way that I can think to draw it, because I don't have a better method. Because one doesn't exist, really. So you might actually see this in some notation where they draw like a dashed line and put a minus sign in it or something like that. So what these electrons are called... Oops, I lost my cursor here. Are called delocalized electrons. And so in resonance structures, the electrons become delocalized. In other words, the electrons aren't constrained to one spot like we've been drawing in these pictures. The electrons in this double bond right here are also in this position too, because in reality, the resonance structure is the average of all of the actual Lewis structures. So this description down here helps us explain that a little bit. How many electrons on average are there between each pair of oxygens? Well, it'd be the equivalent of a 3/2 bond. And there's 2 electrons per bond, so on average 3. And that's the best way we can describe it. Up till this point, you might have thought, well, that doesn't make any sense. How can you get an odd number? Well, you can if you take the average. You could have 2 on one side and 4 on the other, or you could have 3 and 3. And remember what we said about making things symmetric before, when we were talking about that CO2 molecule? We liked the double bonds, but we didn't like the triple bond and the single bond. Because if you can do that, then that... sorry. I think that's probably Steve messaging me. Let me turn that off. If you can do that, then you get a closer structure. But what you'll probably realize is that at this point, it probably sounds like we're just throwing shit at the wall and seeing what sticks in terms of these models. And yeah, we kind of are. Lewis structures aren't perfect, but they do a good enough job of describing how matter looks that we still use them. Okay? So you don't have to worry about delocalized electrons, but what I do want you to consider is this formula that I have in purple here. So you do need to know that. I don't know if that's in your textbook, but it's described for sure in your textbook, just probably not in terms of a formula. And so when you are trying to figure out what is the bond strength of stuff in my molecule, this is the way to do it. Let's do another example. Let's talk about phosphate. We drew this before. This was our phosphate. And we said that this was the best Lewis structure that we could get. Uh-oh. Yeah, you can't see that, can you? There you go. Now I'm going to draw some, like, caricatures of it, because I don't want to sit here and draw the whole thing over and over. So you can imagine that these are my resonance structures for phosphate, right? And these all have oxygens around them. I guess I could put the oxygens in. I'm not going to put the electrons in, though, because that's just going to take too long. And so I've drawn all the resonance structures for phosphate. And so let's apply the same thing. I'm going to just pick... let's pick the bottom position, because why not? I'm going to pick the same position across all the molecules. And then we're going to calculate the formula here. So there are 1, 2, 3, 4, 5 bonds over 4 positions, or 4 structures. So each bond represents what we would call a 5/4 bond, or 1.25. If you want to use decimals, that's fine. In other words, because there are 4 positions, I have like an extra quarter of a bond in each of these positions. Now, with electrons, it's a little harder to get the numbers here because that's not going to work out to be a whole number. But remember, electrons are also delocalized, which means that on average, they will just spend more time in certain places than others. So you can calculate the bond strength in terms of positions in resonance structures just like this. So now you know that when you have resonance structures, you can figure out what the real structure looks like. Now this is useful because... we'll write this down here. Bond strength relates to bond length. Okay. What is the length of a bond? Well, remember that we have Coulomb's law. Coulomb's law says that, oh, okay, if I have different charged things, and I do have different charged things because this is going to be the nucleus of my atoms, and this is the electrons between them in my covalent bond. If I make R smaller, the strength of attraction goes up. So what this means is that if I have a single bond, that's the least amount of attraction because I have the least number of electrons there. So R is going to be really big for a single bond. So single bonds are long. I misspelled single. I'll write this somewhere else, actually. So let's just do... I want to keep that I just wrote on the board there. So single bond are longer. Double bonds are in the middle, and then triple bonds are shorter. And the reason for this is because if this is my nucleus, and this is my nucleus of the 2 atoms that there are there, in a single bond, I'd have 2 electrons between them to provide some attraction. If I had 6 electrons in between them, these guys would all repel each other. Oh, you can't see. I'm sorry. If I had 6 of these electrons in here, they'd all repel each other unless the attractive nucleus, or the attractive force of the nucleus was closer. So I can make that closer. Oops. I'm trying to get my select tool. There we go. So if I make it closer... whoop, there we go. If I do that, now this will hold them in place, and the bond length goes down. Now, these aren't just these three options are the only options, single, double, and triple. When we were solving for these numbers, and I got like 1.25, 1.25 would just represent a bond. Sorry, I have this marker on them. 1.25 would just represent a bond that's somewhere between a single and a double bond, like right there. And then we had the 1.5 bond, which was the 3/2 bond for ozone. So in other words, the oxygen-oxygen bond length in ozone is somewhere between a single and a double bond. And its strength would be somewhere between a single and a double bond also. And just in case we wanted to categorize what the strengths are, we're going to talk about bond strength in 162. Single bonds are weaker than double bonds, which are weaker than triple bonds. Triple bonds are really strong. And the reason for that is because there's just much more attraction between more electrons and closer nuclei due to Coulomb's law. So your textbook might ask you questions about bond strength and length, and what it is going to ask you will be things like, which is stronger, the bonds in this molecule or this molecule? And so you want to look to see this gradient right here. Single bonds are weak, double bonds are in the middle, and triple bonds are strong. But if you have resonance, you're going to get a number that falls between one of these, and you should be able to sort them. And that's a really useful tool to have. For instance, let's ask the same question about ozone with O2. What is the stronger oxygen-oxygen bond? Here's ozone. I'm going to draw one of the resonance structures of ozone. And we know that it has a 3/2 bond because of its resonance. Let's draw oxygen. Oxygen doesn't have any resonance structures. This is just its oh. God, I'm the worst at this. I'm sorry. Please keep yelling at me. I apologize. If I see chat scroll, then I will notice, oh, I fucked up, and I'll fix it. There's the resonance structure for ozone, or one of them, and it has a 3/2 bond. Oxygen has a double bond. Which of those numbers is bigger, 3/2 or 2? The one with the bigger bond is going to be the stronger bond. All right. I realize I made an oh-woo face there with my OO, but that is the oxygen-oxygen bond in O2 will be stronger than the oxygen-oxygen bond in O3. And because the bond is stronger, it's also the shorter OU bond. There you go. Now we can fill the chat with a woos. Alright. That's really all I have to say about resonance. Let's do some more examples here. What I want you to do is I want you to draw nitrate. NO3-. Draw all of the resonance structures that you can. I'll give you a hint. There should be 3. And then I want you to calculate the bond. I'll call it the bond order because that's what it's actually called. Is it 1? Is it 2? Is it a half? Is it 3/2? What do you get for your calculation? Draw the Lewis structure and type in the number in chat. And then we'll draw pictures of it and see if that's right. All right, how are we doing? Hopefully almost there with the Lewis structures. We'll give you just a minute more to finish up, and we'll go over the answer. All right, so hopefully you drew these for your resonance structures. I didn't have my brackets on here. For whatever reason, I don't know why that wasn't included. So these should have brackets around them with minuses around them. But let's describe the bond strength by choosing a location. I'm just going to pick this one arbitrarily. You could do this for any one. And let's calculate the number of bonds that are in there. So there's 1, 2, 3, 4. Over 1, 2, 3 Lewis structures. And so what I would say is that the bond strength between N and O in this molecule is a little bit stronger than a single bond, but not quite a double bond. It's more like a 4/3 bond. Damn it, Steve, stop messaging me. Sorry, you can't hear it, but it's pinging in my ear. All right. So that's how we use resonance structures to describe bonding. And remember, if you can move electrons around and get equivalent structures, those are resonance structures. All right. I'm going to leave these examples for you to try on your own. Because I do want to talk about geometry today, and I only have 20, 30 more minutes to do it. So you draw the Lewis structures for SO3 and SO3 2-. Draw as many resonance structures as you can. Which one has the shorter SO bond length? And then you can try drawing benzene. Benzene is a special molecule that has 6 carbons in a ring. And the bonds alternate single, double, single, double, single, double. You can try drawing those on your own. But I do want to get on to the next topic, which is geometry. So that I have a shot at finishing this on Thursday. So let's continue on. So up until this point, we've been drawing all of our Lewis structures on paper as if they're just flat. But in reality, molecules are 3-dimensional, just like we are. If molecules only existed in 2D, then when we turned sideways, we would completely disappear like Paper Mario. And obviously that's not what happens, because I turn sideways and I'm quite wide. So we need to understand how molecules exist in 3D, because that will have very important consequences for things like enzymes and protein structures and stuff like that. So let's talk about geometry. How do molecules exist in 3D? Well, all molecules have bonds, and all molecules have electrons around them. Those entities all repel each other, and they repel each other in a very simple way. I just read the chat here, and I got distracted here. I forgot your question. I apologize. We have 2 Lewis structures of the same molecule. One has a formal charge of -1, and the other is +1. Which one is better? I don't know if that is possible to have something that's -1 and something that's +1. Because the overall formal charge has to add up to the molecule itself. And -1 and +1 don't equal each other. So I guess I'm confused by your question. But I don't think that situation can occur. If that's the answer to your question, then great, I guess. Anyway, back to shapes. Shapes exist in molecules just like any other place. We're going to have properties that we can measure, such as bond length, which we were just talking about. We have bond angles, which can also be measured, but using X-ray crystallography. And all of these things help us determine how molecules are structured. And we can use that for things like catalysis, structuring enzymes, building better drugs that will fit the topography of, like, I don't know, whatever brain or neurological membrane that we need to match them to. If we know the structure, we know its geometry, and then we can fit the molecule in there like a puzzle piece, and then they can interact. How are bonds measured? We measure bonds in angstroms. An angstrom is 1 × 10⁻10 meters. Another common unit is the picometer, which is 10⁻12. Something that I just remember. I don't like the unit angstrom because it's not SI, but picometers is pretty good because that's a unit that we are familiar with. We can conceptualize a meter. The conversion that I have memorized is just that there are 100 picometers in an angstrom. So when you look at bond lengths, you're going to look at numbers that are going to be roughly on the order of 100 or so picometers. For angstroms, it's going to be roughly on the order of 1 to 2 angstroms. Bond angles are measured like any other angle. They're just measured in degrees. To have a bond angle, you have to have 3 atoms connected to make an angle in the first place, and then you'd have the angle between them. Bond angles generally will be... I know. I personally like radians, but most people don't, I guess. Bond angles generally will fall very close to what you would geometrically expect. For example, if this circle that I just drew was 360 degrees, and I split it into 3 parts right here, each of these should be roughly 120. There will be deviations. For example, in this case, the deviation arises because this double bond pushes these electrons further apart than the single bonds push back. And the reason for that is just there are 4 electrons in this space, whereas there are 2 electrons in each of these spaces. And the 4 electrons exert more force. They just push a little harder. We're going to see a bunch of examples on that, and I'll show you all the bond angles as we do the geometry. But what we need to do is actually assign the geometry and figure out how to determine it. And so that's where VSEPR theory comes in. VSEPR theory is short for what's known as valence shell electron-pair repulsion theory. Let me just get the name on the board here. And we know what all of those words mean. Believe it or not, I have the wrong pen. There we go. So valence shell just means, hey, those are the electrons on the outermost layer of the atom that are involved in bonding. Electron pair means that all of the electrons we've been dealing with the exception of resonance, because resonance can be weird, all of them have come in pairs. They're either paired in a bond, or they're a non-bonding pair on the outside. And then finally, repulsion theory is just electrons repel. And because we have explained why this happens, these shapes occur because electrons repel from each other. We call it a theory. It's not a law. We know what's going on. Electrostatic charges that are the same magnitude or the same charge, so positive or negative, will repel from each other. So VSEPR just says, if I have 2 entities around a central atom, and they both contain electrons, they will fly apart as far as they can in terms of a bond angle. The same will be true if there are 3 entities, and 4 entities, and so on. So for 2 entities, these objects will repel as far apart from each other as they can, and form this angle, 180 degrees. If I had 3 entities around the central atom here, let me just do that. The same thing occurs. It's just that we've spaced them out a little less distantly. And the angle that would form there is 120. And then we just keep doing this as we add more and more entities to the central atom. Although 4 is the point where something becomes unique. So this is what you might think happens for 4. Where you'd say, oh, okay. I'll just put everything in a square and get 90. But in reality, what happens is you get a tetrahedron that starts to use all 3 dimensions. And there's that number I mentioned before, 109.5. Since 109.5 is bigger than 90, we never see anything that looks like this plus symbol. At least not with 4 things around it. It turns out with 6 things around it, there is a way to get there. And we'll show that. All right. Now, what are the things that take up space? So in my little drawings here, I just drew kind of a purple blob. In this purple blob would be anything negative. Okay? Now, if I were going to list things that were negative, that would be stuff that you would see in a Lewis structure around the central atom. And so that could be an electron pair, or it could be a bond. Oops, I clicked on this thing. So it could either be an electron pair, or it could be a bond. Regardless of what it is, electrons live inside it. And electrons repel other electrons, which is where valence shell electron pair repulsion theory comes from. So our job is to determine how many electrons we can squeeze in each of these locations, and then determine geometry based on that. So if I have my generic shape down here, here's my circle, and I have, we'll just draw X's around this. Here's where my electrons are. What occupies these X's that has a negative charge? Well, it could be a bond. Any bonds to any other atoms have electrons in them. Now, if I make a single bond to my atom, or I make a double bond to my atom, it doesn't matter in terms of space. The space that is occupied by this bond is roughly the same, whether it's single or double. So we're just going to say, okay, whether it's single bond, double bond, or triple bond, or whatever, we're going to call that a region of electron density. The other thing that could be attributed would be any pair of electrons that are non-bonding. Those also take up space too. So in our little sketch over here, each of these is a domain. This is a domain where electron density is found, either because there are electrons in a bond, again, the type of bond doesn't matter, single, double, or triple, or because electrons for a non-bonding pair reside there. So we're going to call these electron domains, or electron groups, depending on which textbook you're using. Some say domain, some say group. I like domain myself. But group, I think, is more universal to the text that we have. So our first task to figuring out the geometry of a shape is to count the number of electron groups around a central atom. And so what you'll have to do is draw the Lewis structure, and then identify the number of groups around the structure that you drew. All right. And the way that we're going to do this is we're going to click on the PHET simulator, which I am going to post the link for, because this is super awesome. So you can play along with this if you like. And let me see if I can window capture it. Here we go. I didn't quite get all of it, though. That's probably okay. Okay, so now I can just do... There we go. All right, so let's do a model here. And so what you can see is I have two generic atoms just bonded to a central atom. If I pull one of them, the other one gets repelled away. How far away does it go? Well, if I do this, no matter where I push this, it always gets repelled away to 180 degrees because electrons repel, and they want to adopt a distance that is as far apart from the other electrons as possible. Now, it doesn't matter if this is a bond or if it is a lone pair. They will still repel because they both have electrons. If I have three entities around my central atom, that is different than if I have two. Two entities, whether they are lone pairs or not, they will always form this 180-degree angle with two entities. If I put three in... Oh, and again, it doesn't matter if it's single or double. In fact, I could just do this if I wanted to. And I'll still make it linear. This obviously violates the octet rule, but the electrons all follow the same behavior, and the program doesn't check for electron or octet rules. If I put three things in here, I adopt this triangle shape. Again, whether it is singles and doubles, or... I don't know. I could do this... Same thing. I could do this. Same thing. Ooh, that looks vulgar. Let's not do that one. I could do that. Same thing. What matters is that I have three entities. I will always end up with the same general shape. It looks kind of like a triangle, doesn't it? Alright. Let's suppose that I had four things. Now I have a three-dimensional shape where it pops out of the screen here. And again, whether there are four bonds or three bonds in an electron pair, or two bonds and two electron pairs, you'll notice that the general orientation of my molecule still adopts this sort of tetrahedral shape. And then I can do the same thing for 5, where if I spin it like this, now I have a straight line. And then going around the center, I have like a triangle. So I'm going to try and bend this carefully. Well, I lost it there. You have to do this one carefully there. So I'm looking straight down the middle now. And now I have a triangle. So I have a triangle that's sort of in the middle. Around the central here. And then up and down for 5. And then 6 would just be same thing, except it's got a square in the middle. Alright, and you can always substitute any of these out for whatever you want. And the result is the same in terms of where the objects go. They always go lined up along these generic shapes. Okay? So these shapes have names, and the names are given right here. So for something that has two entities connected to its central atom, the shape that we end up with looks like this. And yeah, it's a really useful program. I definitely recommend playing around with it to just see the shapes, because me talking about this and drawing it in 2 dimensions is very different than you manipulating it in 3 dimensions. But if you have the opportunity to draw these on paper, which you're going to have to at some point to answer the questions, you're going to need to see how to draw them properly, and so that's where this comes in. So the filled-in circle is the central atom, and then the hollow circles are going to be my external atoms. There's trigonal bipyramidal, and then octahedral is just up, down, left, right, front, back. There you go. Whenever you draw a molecule, you're going to count the number of electron groups, and however many electron groups there are, 2, 3, 4, 5, or 6, is going to be which template you use. If I have a molecule that has 3 electron groups, I have to use this template right here. If I have a molecule that has 5 electron groups, I have to use this template right here. Okay? So this is how you draw any molecule in 3 dimensions using these templates. Okay? Let's do an example. So I'm going to have to clear the screen. Well, actually, I don't have to clear the screen. I can work down here. So let's suppose that I had this molecule here. I gotta make sure that that actually works. Yes, okay. I don't want to get an odd number of electrons and then not be able to draw that. So if I wanted to draw this molecule, ICl5, I would follow the Lewis structure rules like normal, and I'm gonna just draw them wherever. All right, so that was 10 electrons to do that. 12, 14, 16, 18, 20, 22. I realize it's behind my head there. 26, 28, 30, 32, 34, 36, 38, 40. I did that right? 8, 16, 20. Yeah, 40. All right. I put 42 electrons down. I have 2 that are left. I got to put them on the central atom. Here's my Lewis structure to start. Is it correct? It looks pretty sketchy to me. It looks kind of sloppy, right? So what I need to do now is I need to figure out where the electrons are around the central atom. So I'm going to circle all of the either bonds or non-bonding electron pairs on the central atom. So let's do that. 1, 2, 3, 4, 5, 6. I only care about the central atom. Don't worry about any non-bonding pairs on the external atoms. Those aren't the central atom. We only want stuff directly touching the central atom because that's taking up space and will determine our shape. Because I circled 6 things, the shape of this must be octahedral. So what I'm going to do is I'm going to go over to the octahedral pattern here. I'm going to go like this. Boop, 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 boop. And I'm just going to stick stuff on there to match my structure. So I was in the middle. I had a Cl in 5 of the positions. And an electron pair in the last one. And then I just fill in the rest of the dots to make my structure complete. And I'm all set. So that would be the correct structure for ICl5. Now, looking at that, you might have just said, oh, okay, it's ICl5. There's 5 things. It must be template 5. But when you draw the Lewis structure and put the extra electrons down, you realize, oh, I have 6 things, actually. I got to use the 6 template. Okay? So what I want you to do is, if you go back to this slide way back here, at the end of the section before we started yesterday, this one right here, all of these have Lewis structures, which I do really want you to draw. Draw them out, and then try and apply them to these templates, and then tell me what the geometry is of them. For example, this one right here, PO4, you should get tetrahedral because there are 4 electron groups connected to it. Because we've drawn this structure like enough times today, we might as well end with it. If I were going to count the electron groups around it, I get 1, 2, 3, 4. Again, I don't care about any on the outside. And also, whether it's single, double, or triple bond, the bond is all in the same spot. It counts as 1 electron group, or 1 domain. Since there are 4 domains, the shape is tetrahedral. Okay? Now, this is called the VSEPR geometry, or electron-pair geometry. Tomorrow, when we come back, what we're going to talk about is something called the molecular shape, which is what the shape of the molecule is if you don't consider what electrons are. So, like, the electron pairs in things are very small, but they exert a force. So they're essentially invisible, so we don't see them as a shape. And that will give us a different type of shape that we're going to talk about tomorrow specifically. But I feel like that's a good spot to end. So let me fast forward this back to where we were. Which is here. We'll clear this really quickly, and then I'll show you this chart. There are all of the electron pair shapes that we talked about today. Later on, we're going to get to another chart, which is this chart, which has more combinations that take into account the effect of electron pairs. Okay, so if you're reading ahead, just be mindful that VSEPR electron pair shapes and molecular shapes are different. And we're going to talk about this in more detail tomorrow. But for the most part, this is just the template that you're going to apply any Lewis structure to. And it works for any shape that you want up to 6. There are templates for 7 electron groups and 8 electron groups, but they're beyond the scope of this class because they're not common. But up to 6 is very common. So you got to know these. And this is how you draw them. Alright, I think that is all the time that I really can cram in for today. So I'm going to put the title card up. Oops. We're not on break, but I will just do this again. Hooray! Yay! I want to thank everybody for coming out to lecture. Lab number 5 will be due on the day of the final. So be mindful of that, because I have to have everything in relatively quickly. So just don't put everything off till the last second. Like, if you're taking the final and then you have to do the lab, like, that's a problem. Oh, I canceled the weekend day. I don't know why that went away. So yeah, as we get towards the end of the quarter, a lot of stuff's going to be coming up really quickly. Quiz number 4 might even be due the day of the final as well. And if you NQA any of these assignments, I do need them by that weekend. Just FYI. And you can't NQA the final and take it later. Just because I need it then. Alright, thanks for coming out to lecture. I'll see everybody tomorrow. Please email me with any questions. I realize we're trying to get through all this material very quickly, so it's going to come at you fast. And if there's anything I can do to help you, please let me know. Have a good night. Stay safe, stay healthy, stay at home.